Hello, ladies and gentlemen. Today we are going to take a look at a new number. It's actually called E. So for our work today, we're going to need your notes, a calculator. If you have a graphing calculator, that's even nicer. And then something to write with, of course. We're going to make a few graphs as well as talk about what is the number E. So remember way back when you were first introduced to pi? Pi was just a symbol, right? But technically it's a number, right? It represents 3.14159, yada, 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 going on forever, right? So it represents this value, this number. And when everybody looks at it, we kind of just know what it represents. Now, what if we kept things in terms of pi like you did in geometry quite often? Could you simplify expressions containing pi? Sure, this says 5 pi squared. That means 5 pi times 5 pi, which would be 25 pi squared. And then you could type this into your calculator as 3.14 squared times 25. We also could even do this with fractions or negative exponents. Remember, when you simplify fractions like 15 over 20, that actually turns into 3/4. We have a pi to the -1. -1 exponents move up onto the top here because he happens to be in the denominator. He'll plop right next to that one. We have pi to the 5th times another pi, making us pi to the 6th. So even though we know that pi represents a number that we could eventually type in if we wanted to, we can just simplify it, leaving it as a pi as well. And you did quite a bit of that in geometry. Now, E, when we think of the letter E for us, it is E, but it also represents a number in math. It's called Euler's number. And E is approximately 2.71828, just like pi is approximately 3.14159. So E stands for 2.71 or 2.72. E is one of the most important numbers in math, along with understanding what I represents, the square root of -1, pi represents. The higher up you go in math classes, the more often you see these numbers or these variables that are representative of numbers that occur quite often in that branch of mathematics. So where did E come from? Well, let's think about that exponential growth formula for compounded interest that we were working with. The amount after time is the principal or the starting amount, 1 plus the rate divided by the number of times it's compounded, and then number of times it's compounded per year times time. So as we increase the compounding time, if you will, so let's say I do this compounding twice a year, and I calculate just this parenthesis part here in a calculator twice a year, so the n would be 2, and we look at that for 1 year, we get 2.25. Now, if I did that every month instead of it twice a year, I do that 12 times a year, 12 times a year, that comes out to 2.61. And as I do it for every day, if I compound or pay interest daily to my clients, I'd get 2.714. And then if I do it every hour for a year, look at what happens. This is how many hours there are in a year. Now I have 2.718. Notice that it was drastically changing here and here, but the more often we compounded, there's not much difference between this number and this number, right? If I type this part in my calculator, I get this value. The more often I compound this, what if I do it every minute for a year? Now look at this number, 2.71827. That's not even that different from each hour, right? The more often we compound this, in fact, if we compound this continuously or every millisecond of a second, you know what I mean? If we just keep going and going and going, and let's say I pretend that this is infinity, what happens is this number gets closer and closer to that E value. This is what E is. Check that out. We were building our way there by increasing the number of times we compounded per year. So with that in mind, that's how E was sort of discovered, if you will, or E became useful when we talk about continuous compounding. So that means growth every chance, every opportunity, every millisecond of the year. So once E was established, well then can you simplify expressions with E? Make sure you get this part in your notes. Well sure, E is just like pi, it's just like x. It's just a variable that represents a number. So if I was going to simplify this expression, what is 2 times 6? Well that's 12. I have E's here. E will be in my answer. What do I do with these exponents here when I have variables and they both have that exponent? When I have the same variables and they both have that exponent, I add the exponents together. So -3 and 5 more would make e squared. Okay, so I have 12e squared. What about this one, b? Oh, I kind of ran into the answer there, sorry. What if we went 24 divided by 4? Well, that's 6 over 1. And if I have e to the 8th over e to the 5th, that means I would have e to the 3rd left on top. Remember the rules, subtract those exponents. And then could you find a value for this in a calculator? Well, sure, if I know a here is 12e squared, and I know e is approximately 2.71, that it actually represents a value or a number, I can type in my calculator 12 times 2.71 squared. So I would start by typing in 2.71 squared and then multiply it by 12, okay? Make sure you find that value because I'm going to look for that part in your notes tomorrow. So what about b? 6e to the 3rd is really my answer. Well, e is 2.71. So 2.71 goes in where the e is in that expression. So I start with order of operations. I do my exponent first here. 2.71 to the 3rd power times 6. And that 2 would give me that value, okay? Again, type that in your calculator, see if you can come up with some values for that. It's not going to be a pretty little number, right? We're going to have some decimal values. We're going to need to round a little bit, but you can evaluate those. Sometimes your calculator even has an E button on it or an E variable that's already on it. Check that out. Maybe your calculator already has that. So can we simplify this expression? Well, this one has an e in it as well. We have 4e to the 2x all taken to the 3rd power. So remember our rules of exponents. 4 to the 3rd power is something that I would calculate first. And then what do I do when I have powers onto powers here? Well, I multiply those. This becomes e to the 6x. 2x times 3 is 6x. So 4 to the 3rd power is 64 e to the 6x. So that's how I would leave that expression simplified. Can we type that in our calculator? No, because we don't know what x is. We can take e to the 6, but that's e to the 6x. So is x 10? Is it 15? Is it 5? Is it 1.8? Who knows? So we'll just leave our answer like that. What else could we do with E? Well, now that we know E represents a number, you know what? This graphing stuff we've been working on, we can still continue to do that as well. So now we need to make 3 graphs to put in your notes here. They are functions that have E in them, okay? So let's graph using the same technique we were graphing before with the exponential growth and decay. This is our original graph. This is what I want to graph, y equals e to the x, okay? Now, e to the x, that, ladies and gentlemen, what does that look like? Well, remember, e is just 2.71, right? So if I do my key points, I end up with plugging in 0, e to the 0, anything to the 0 power is 1. And then if I plug in the number 1, e to the 1st power, e to the 1st power, that's 2.71 to the 1st power is still 2.71. So you're not going to find e on a graph, right? But remember, e represents that decimal 2.71 approximately. So my parent graph, and then notice this graph that we were asked to make here doesn't really have anything that's moving it, shifting it, stretching it, flipping it, any of those things that we've discussed. My parent graph looks like this: 0, 1, 1, 2.7. So this, guys, is an exponential growth graph. How do I know that? How do I know that to connect the dots in this way? Well, because E is 2.71. So it's like we're being asked to do this. And remember, we talked about anytime that base is bigger than 1, we're talking about exponential growth. So what is E? E is just 2.71. So we're talking about an exponential growth graph, just like the other ones we were making, okay? So is this representing growth or decay? This would be growth. I can see it. I know that the base is 2.71, and that makes sense. Asymptote, where would that be? At y equals 0. That's where this leveling off spot is over here. And remember, there's nothing being added or subtracted here to move that asymptote for us. Domain, all reals. And the range, y is greater than 0. Yeah, that whole graph stays above my asymptote at 0. So that's how we make these graphs with E in them. Now, just like all the other ones we've been talking about, they could also shift a little bit. So check this out. Here's another one we should get in our notes. So this one is y equals 2 times e to the x plus 3. So just like the other ones we were making, we have an e, we have a shift that's happening in here, we have a 2 in front. All those same rules still apply. So our parent graph is still going to be just what's the base and what's the power. So y equals e to the x. So my key points are still going to be the same. 0, 1, 1, 2.71 or 2.7. So my parent graph is the same as the last one we just drew. So I'm going to sketch that one in right here. Growth graph, here we go. There's the parent using our key points. Now let's identify what's happening in terms of how this function is changing or how we need to modify this graph. See that 2 in front? That is our stretch. Okay, this is the graph we were actually asked to make. We have the parent graph first so that we can move those points. The vertical stretch of 2 means each of these y values here are going to be multiplied by 2. So I have 0, not up to 1, 0, 2, and 1, 5.4, right? 2.7 times 2. So we're going to do 0, 2, and 1, 5.4. And always that's approximately, right? Here we go. Oop, missed the dot. Here we go again. There we go. Stretching. There's my stretch. There's where I'm located after the stretch. So I had the parent. Now I'm stretched. Now I need to do what this part up here is telling me to do, and that's telling me to move my points left 3. So I'm going to take these same dots that I just finished with and just move them over 3 units. 1, 2, 1. Let's try that again. 1, 2, 3. There we go. I lost my 0.4 there. And then this one at 2, 1, 2, 3. Now my asymptote didn't move, right? I don't have any shifting up or down. So this is my final answer. I just took that whole boomerang, if you will, and moved it over to the left and made it be a little bit steeper. Is it growth or decay? It's still growth, right? I mean, I still see it have that starting real small and then swooshing way up. Asymptote, still at y equals 0. So my domain's still going to be all reals, and my range is still going to be y is greater than 0. Okay, so now let's take a look at one more. This one's a little tricky, so I hope you're still listening and didn't fast forward the video or think, that's good enough, because this one has a negative up in that x, and that's different than a negative in the front that I flip over, okay? So let's take a look at the parent graph again. Our key points are still going to be the same, 0, 1, 1, 2.7. For my parent graph of my function. So here's the parent graph for y equals e to the x. The base and the exponents all you keep for the parent function. From there, we identify things that are happening. I see a negative. Remember in our list we made, that was the next thing that we looked for. We looked for that stretch, which we don't have, and then we looked for that negative. I do see a negative sign. The negative doesn't happen to be in front of the e like this. If it's in front of the e, then we flip it over the x-axis. But the fact that that negative's up in the exponent tells me something huge. We're going to flip that over the y-axis. Because it's e to the negative x, the negative sign is in front of the x, we flip it over the y-axis now. So this point, ladies and gentlemen, will no longer become 1, 2.7. In fact, now it's going to become negative 1, 2.7. He's going to flip over, whoop, the y-axis and just pop over here. He was 1 unit away. He's going to stay 1 unit away. This dot, which was on the y-axis, when you reflect something over a y-axis like that, it doesn't move, right? Because it's on the y-axis. You did a lot of reflections in geometry as well. So this is my flipped over, I'm going to put an F there, my flipped over version of my parent function to take care of this negative x business. Then I need to move him up 1. So I take this function where I'm at right now, and each of the points, the 2 points I have on here, I'm going to move up 1. So up 1 for this dot, this guy right here, up 1 here. So my new function, oh, that kind of went straight up, sorry. Leveling off here, oops, leveling off here. My bad, little sloppy. We now have our final answer. I better label that final. There we go. And notice what this looks like now. This does not look like a growth anymore. It started out, if I read just my final graph, I'm starting out really tall here, or really high on the left-hand side, and then it's kind of swooshing downwards and getting really, really small. Because of that, we're saying that this is a decay representation, okay? So growth or decay, I'd say this guy is decay. The asymptote will be at y equals 1. So you can tell my graph is a little sloppy here. This line should have went right on top of that 1. Why do I know that that's 1? Once again, this up or down movement here shows me where my asymptote is. The domain is still going to be all reals. Now my range is that graph above the asymptote or below. That graph is above, so I'd say my range y is greater than 1. So just like all the other graphs we've made, E is no different. E represents a number. We can simplify with it like it's a variable, and we can graph with it like it represents that base for exponential growth. Okay, so I want to thank you very much, ladies and gentlemen, for taking good notes. We'll work more with E. Again, I want to thank you for paying close attention in this video. Thanks. Bye. Kincaid out.